Good morning, students. I am Professor M.V.S.N. Sharma. In today's class, we are going to discuss a variant of a standard radar which is used to continuously observe the locations of an incoming target, that is a tracking radar. So, in this class, we shall see what is the basic operating principle of a tracking radar, what are the types of radars available, what are the techniques used to improve the target detection, and some examples of tracking radars. Before we go into the details, first let us enumerate the functions that can be done using a radar. As we already know, a normal radar can be used first to identify whether there is any target or not. Then we can also find its distance from the radar, that is range. This is measured normally from time delay of the pulse transmitted to the echo received. The second parameter that can be measured using a normal radar will be velocity of the target. For this, we take the help of Doppler frequency shift between the transmitted and received signals. The third one that can be done with a normal radar will be azimuth and angle information. This is obtained from the antenna pointing direction. The antenna is placed over a compass, and the way the antenna is moving in the horizontal direction and in the vertical direction will be indicated through a pointer on the compass to get this angle information. You can see my finger as though the dipole placed before the reflector antenna. If this has to be rotated, you can rotate this in a circular manner, keeping the vertical polarization like this. If you are doing this way, then this field is known as nutating field. A rotating field is one which causes the plane of polarization to rotate. In the earlier case, we are always keeping the vertical polarization of the field and rotating the field in this manner. But now, in the present case, we are going to rotate the antenna in an axis like this. So, at certain point, the field has vertical polarization. At another time, it will have horizontal polarization like this. Again vertical, again horizontal like this. It's going to be rotated around this. Then we call it as rotating field. You can see in this slide what is the comparison between these two types. A rotating polarization can cause amplitude of the target echo signal to change with time, even for a stationary target on axis. So, you feel nutating field may be better, but nutating field is more complex compared to a rotating field. So, we prefer to use a rotating field wherein the dipole or the field will be continuously rotating and the plane of polarization is going to change. That is easier for the regular operation. A typical conical scan rotation speed might be in the range of 30 revolutions per second. That means in 2 seconds it's going to complete the one rotation around the target with several beams placed adjacent to each other. The same motor also drives a 2-phase reference generator with electrical outputs at the conical scan frequency that are 90 degree apart in phase. These two outputs serve as reference signals to extract the elevation and azimuth errors. Now, let us concentrate on the receiver. The receiver is a superhet receiver except for features related to the conical scan tracking. The error signal is extracted in the video after the second detector. Range gating eliminates noise and excludes other targets. The error signal from the range gate is compared with both the elevation and azimuth reference signals in the angle error detectors. From this, what we can understand is that in the superhet receiver, as we know, there will be a detector after the IF amplifier, which eliminates the carrier and gives the modulating signal output. So, we will have a video amplifier after this. That will be the error signal which is used to control the antenna rotation. Similarly here, the echo signals coming from different ranges are processed in different receivers. For this, we will have separate time domain filters which will be receiving the signals from different ranges. By this, we will be able to eliminate lot of unwanted signal from the stationary targets at different ranges. So, range gating eliminates noise, and the range information is obtained from the sum channel output of the antenna. These can be used as a reference so that azimuth and elevation angle informations can be obtained by comparing the received signals from the sum signal in the error detectors. Let us understand some operational aspects. The angle error outputs are amplified and used to drive the antenna elevation and azimuth servo motors. The video signal is a pulse train modulated by the conical scan frequency. It is usually convenient to stretch the pulses before low pass filtering so as to increase the energy at the conical scan frequency. To perform analog to digital conversion, pulse stretching is accomplished by sample and hold circuits conventionally. The same technique is being used here also. The PRF must be sufficiently large compared to conical scan frequency for proper filtering and avoiding inaccuracy of the angle measurement. The PRF must be at least 4 times of conical scan frequency, but normally we go with 10 times the value. We normally go with AGC, that is automatic gain control. It has the purpose of maintaining constant angle error sensitivity in spite of amplitude fluctuations or changes of the echo signal due to change in range. That means the output of the AGC is going to be a constant signal even though there are variations in the input. AGC is a negative current supplied to the amplifier to adjust the gain so that the input fluctuations are absorbed by the variations of the gain of the amplifier, and hence the output will have uniform value. In that sense, AGC can be considered as an amplitude equalizer. AGC is also important for avoiding saturation by large signals, which could cause the loss of the scanning modulation and the accompanying error signal. Here, the AGC will provide a very low gain to the amplifier, and thereby the output is within the saturation limits, and thereby still with large input you will be able to track the targets properly. The practical point here is the gain of the AGC loop at the conical scan frequency should be low so that error signal will not be suppressed by the AGC section. Only the unwanted signal is not amplified much. Here you can see how conical scan will have the output signal if the beam axis and the target axis are same. All target returns have the same amplitude under this condition, and there will be zero error signal. If that is the case, the antenna direction should not be changed, and here we say no action is required. In such a case, you can see the return pulses in the graph shown. A practical conical scan is shown here. As the antenna is rotated, you can see a large amount of signal at certain angular locations and reasonably small ones at other locations. The adjoining graph indicates these variations. Because of the rotation of the squinted beam and the target's offset from the rotation axis, the amplitude of the echo signal will be modulated at a frequency equal to the beam rotation frequency. The amplitude of the modulation depends on angular distance between the target direction and the rotation axis. The location of the target in two angle coordinates determines the phase of the conical scan modulation relative to conical scan beam rotation. This scan modulation is extracted from the echo signal and applied to a servo control to position antenna axis on target. So we require two servos. When the antenna is on target, the conical scan modulation is of zero amplitude. So here we will have a comparison between sequential lobing and conical scan in terms of their disadvantages. In the case of sequential lobing, angle accuracy can be no better than the size of the antenna beam width. Variation in echo strength on a pulse by pulse basis changes the signal level, thereby reducing tracking accuracy. The antenna gain is less than the peak gain in beam axis direction, reducing maximum range that can be measured. The disadvantages of conical scan are as follows. 1. The antenna scan rate is limited by the scanning mechanism, whether it is mechanical or electronic. It is sensitive to target modulation, mechanical vibration, and wear and tear due to rotating speed will also give rise to certain limitations. Simultaneous lobing with a single pulse, angular coordinates can be obtained. Maximum unambiguous range is limited only by pulse repetition frequency. And monopulse, if you are going with this, it is free of mechanical vibrations. Errors due to amplitude fluctuation of target echoes are greatly reduced. So, monopulse means with a single pulse you will be obtaining angle coordinate or even coordinates. It is defined as one in which information concerning the angular location of a target is obtained by comparison of signals received in two or more simultaneous beams. A measurement is done based on a single pulse. So we give the name as monopulse. But many pulses are employed to increase the accuracy. The accuracy is not affected by amplitude fluctuations of target echo. Out of the several types possible, most popular monopulse is amplitude comparison monopulse. What is this monopulse is? Amplitude comparison monopulse compares the amplitudes of the signals simultaneously received in multiple squinted beams to determine the angle. The required squinted beams are generated by two slightly displaced fields on a parabolic reflector. While the difference pattern is for angle measurement, the sum pattern of the antenna is used for range measurement. Signals received from the sum and difference patterns are amplified separately. They are combined in a phase sensitive detector to produce the angle error signal. The sum signal is used to get the range and the sign of the angle of the incoming target. Let us see what is this phase sensitive detector which is used in the case of the monopulse. This system contains a phase sensitive detector that compares two signals of the same frequency. So basically it is a non-linear device. The output indicates the direction of the angle error relative to the bore side. Though phase comparison is done, the magnitude of the angle error signal is determined by comparison of amplitude signals. How does a 2D monopulse work? What we mean is two-dimensional monopulse. That means it gives the information of both the angle coordinates with a single pulse. Here, let us first understand some new components that are used. One is a hybrid junction, and here the inputs are 2 and the outputs are 2 in this case. What are the inputs? The inputs from the feed horns will be given to hybrid junction. So with the two inputs there can be two outputs. One output is the sum channel, the other output is the difference channel. So using these type of hybrid junctions in 3 numbers, we can get both angle and range information with a single pulse. If all the 4 received signals are combined, A plus B plus C plus D, then we get the sum signal used for range. Then if you take the outputs of the feed horns, A plus C into one hybrid junction, B plus D into another hybrid junction, then the difference of these two signals will give rise to azimuth information. That means first 2 channels are summed up, then the difference of these 2 sum channels will be used to get azimuth information. Similarly, another 2 channels are summed in another hybrid junction. The difference of these 2 outputs are taken from one more hybrid junction to get the elevation information. So as you can see, A plus C will give rise to the center point of the one set of feed horns. B plus D information will give rise to another center point. The difference between these two will give rise to azimuth. Similarly, A plus B and C plus D channels are summed up separately. Then these two are applied to one more hybrid junction to get the difference for the elevation information. So we can say that we are going to use difference of the sum channels to get the angle informations. The hybrid junction in waveguide form or in microstrip form are shown in the diagrams here. Basically, they are magic keys or rat race. So port 2 and 3 will be used to get the inputs, whereas port 1 and 4 can be used to get the outputs. One sum channel, the other one difference channel. In the context of this rat race, you can go with 1 and 3 as inputs, 2 and 4 as outputs, or vice versa. A complete block diagram of a monopulse to be used for 2 angle coordinates is shown in this slide. The antenna outputs are given to 3 different hybrids. One is for sum channel output, another one is for elevation, the third one is for azimuth. All of them are separately processed, and the azimuth and elevation error signals are given to servo motors to adjust the antenna location properly, and the range information is obtained from the sum channel. What are the precautions in this case? It is important that large relative phase differences do not occur among the 3 channels. A typical value generally tolerable will be 25 degrees of phase for proper performance. AGC is required to maintain a stable closed loop system for angle tracking and to ensure that the angle error signal is not affected by changes in the received signal amplitude. Practical issues are generally a Cassegrain reflector is normally used to place the microwave circuitry at the back of the antenna. Feed system can be easily supported with this. The greater the squint angle, the better will be the accuracy of the angle measurement. What is the trade-off? The on-axis gain of the sum pattern decreases if the squint angle increases. So there will be range inaccuracies if you try to improve the accuracy of the angle measurement. Simpler and more compact feed system can be obtained by using higher order waveguide modes to obtain independent control of the sum and difference patterns. This is one case where a waveguide is used with the several modes propagating simultaneously. Normally we see that a rectangular waveguide is operated at a single mode, which is the dominant mode, that is TE10. But here we go with TE10, TE11, TE20, etc. to get sum and difference channels of the 4 feed horns simultaneously using a single waveguide. Now let us see another type of monopulse, which is phase comparison monopulse. 2 antenna beams are used to obtain an angle measurement in one coordinate. Here the 2 beams look in the same direction, whereas in the earlier case they looked at slightly different directions. Due to displacement of the antennas, the 2 received signals will have slightly different phases but same amplitude. But the phase difference will be quite small if the electrical spacing between the antennas is small. So angle information can also be extracted in a phase comparison monopulse by employing sum and difference patterns and processing the signals similar to the case of amplitude comparison method. An analysis of the sum and difference patterns for the phase comparison monopulse shows that a 90-degree phase shift has to be introduced in the difference signal so that output of the phase sensitive detector is an error signal whose amplitude is a function of the sine of the angle of arrival from the target measured with reference to the perpendicular to the two antennas. What are the limitations of this phase comparison monopoles? Effect of grading lobes due to wide separation between the antennas. Ambiguities in the angle measurement. So, to overcome these problems, a portion of the parabolic reflector is sliced off to reduce this physical spacing between the two antennas. Amplitude and phase comparison monopulses. What are the plus and minus points of these things? A total of 4 hybrid junctions generate some azimuth and elevation difference channels. Range information is extracted from the output of the sum channel after amplitude detection. The angular error signal is obtained by comparing echo amplitudes, which actuates a servo mechanism to position the antenna. The angle of arrival is determined by comparing the phase difference between signals from the two separate antennas. Antennas of phase comparison are not offset from the axis. Let us have a comparison between the two types of trackers we came across. In phase comparison, 4 antennas are placed in upward direction and its side lobe levels are high. Sequential lobing suffers more losses with complex antenna and feed system. Amplitude comparison has high SNR. It has higher precision in target tracking due to the absence of target amplitude fluctuations. Angle error in two coordinates can be obtained by a single pulse. Conical scan integrates number of pulses and then extracts angle measurement, but there will be opposite process in monopulse. That is, each pulse gives rise to angle information. For different pulses, we are going to integrate or take an average of this data. Whereas in conical scan, initially all the pulses are integrated, then the angle measurement is done. Let us compare about the SNR. The SNR from a monopulse radar is greater than that from a conical scan, since it views target at the peak of the sum pattern. In that sense, the SNR of a monopulse is 2 to 4 dB greater than conical scan. Accuracy. Due to the high SNR, the range accuracy is also high in monopulse. The accuracy is not affected by fluctuations in the amplitude of the echo signal. Both systems are degraded by the wandering of the apparent position of the target caused by glint. What is this glint? We shall see towards the end. It is basically noise. What type of noise? We shall see later. Let us compare again in terms of complexity. Monopulse is more complex of the two. Conical scan has to rotate or mutate the beam at high speed. The Cassegrain is a popular choice for monopulse. A space-fed phased array can implement monopulse by using multiple feed similar to Cassegrain. Let us see in terms of minimum number of pulses. A monopulse can perform on the basis of a single pulse. For a phased array, one pulse is sufficient. But normally, a number of pulses are usually integrated. The conical scan tracker requires minimum number of 4 pulses per revolution of the beam to extract an angle measurement in 2 coordinates. The monopulse first makes its angle measurement and then integrates a number of measurements to obtain the required SNR. The conical scan integrates a number of pulses first and then extracts the angle measurement. susceptibility to ECM, electronic countermeasures, basically for jamming. Conical scan tracker is more vulnerable to spoofing that takes advantage of its conical scan frequency. That means the jammer sends a huge amount of signal at the conical scan frequency, which is a low frequency. Hence, he will be able to pump in good amount of signal and the radar can be easily jammed. And we know very well, it's not easy to change the conical scan frequency because the antenna is rotating by that and the servo motors are designed already for that. Hence, it is very difficult to avoid jamming in case of conical scan. It can also suffer from deliberate amplitude fluctuations. A well-designed monopulse is hard to deceive. The application. Monopulse trackers should be used when good angle accuracy is needed. When high performance tracking is not necessary, the conical scan tracker might be used for its low cost. So before we end, let us see what is this glint is. It is angle noise or angle fluctuation. It occurs with complex targets that have more than one scattering center within the resolution cell of the radar. A single point scatter, such as a spear, does not show glint, whereas in an aircraft there are several points of scattering and hence there will be glint. The greater the target in angle, the greater is the glint error. Here in this picture, you can see first missile guidance system to employ monopulse technique. It was developed in year 1953. Similarly, you know very well about the use of Patriots to counter the Scud missiles. So Patriots will have a phased array system which is used to track several targets simultaneously. You can see the details of Patriot air defense system in this slide. A monopulse or a phased array radar is used if extreme accuracy is needed. Its improved interference immunity, resolution, radar signal processing and angle accuracy made it imperative in all modern tracking or guidance systems. Yeah, the following are the answers for the questions on tracking radar.
How monopulse tracking radar is free of mechanical vibration?
How monopulse tracking radar is free of mechanical vibrations. In a conventional radar, the pulses are sent while the antenna is moving from one location to another location. So, the mechanical vibrations due to antenna moment will be contained within these transmitted pulses and the echo is also having the same thing. On the receiver side, the received signals are first added together or integrated together and then we get the information on the range or angle. So, the conventional radar will have the difficulty of these mechanical vibrations. Whereas, in the case of a monopulse, only one pulse is sent at a time and when pulse is being sent, the antenna vibration does not come into picture and the received signal of this pulse is processed and the information is directly displayed on the screen. So, the mechanical vibration does not come into picture for the single pulse case. When we are taking several pulses together, then only the vibration aspect comes into picture. Right.
How the accuracy of monopulse tracking radar is not affected by amplitude fluctuation of target echo.
How the accuracy of monopulse tracking radar is not affected by the amplitude fluctuation of the target echo. The amplitude fluctuation of a target occurs because the radar looks at the target differently for different pulses due to its movement in a normal case. But in the case of a monopulse, the radar looks at the target at only once. So, whatever angle it has, that will be processed and you are getting the display of that. So, there will not be any amplitude variations
of the target.
Why is the echo modulated by conical scan frequency?
Why is the echo modulated by conical scan frequency in a conical scan system? It is due to the rotation of the squinted beam of this antenna system.
Why do we use several pulses though a single pulse is enough in monopulse?
Why do we use several pulses though single pulse is sufficient in case of a monopole? Yes, by the design a single pulse is sufficient to get the information on the range as well as azimuth angle or elevation angle or both depending on the capability of the monopulse. That is how the name has been given as monopulse. But with one pulse whatever data we get will not be very accurate. So, to get more accuracy of our information we normally send 3 or 4 pulses towards the target at a time and try to process the signals after the data is established.
Why do we need AGC in a monopulse system?
Why do we need AGC in a monopulse? AGC is always required to stabilize the receiver chain. So, here also we use the AGC to have a stability of the receiver closed loop feedback system. This is very much useful for the angle tracking and to ensure that the angle error signal is not affected by changes of the received signal amplitude. Thank you.